one part that was missing from the introduction, but that's normal because it happened like a month ago, is that I'm also PG Bouncer maintainer since like a month ago. And this talk will also include some PG Bouncer stuff. So what I'm going to talk about is mostly load balancing, mostly about load balancing across Postgres servers, and a bit about read replicas, and a bit about Citus, and some low-level details about how canceling queries works in Postgres under the hood, and then also a bit about PG Bouncer. So first of all, let's start a bit simple. What is load balancing? Well, it's quite simple. You share a workload across servers. Probably most of you know about this. And the idea is that different servers handle independent requests. So why would you want load balancing for Postgres? Well, the main thing is you want some performance improvement. So you can scale out reads with Postgres if you're using read replicas, and you can scale out writes with Citus, which is an extension for Postgres. So let's go a bit deeper into why would you even want to scale out reads or writes? Well, if you have some clients, connect queries to Postgres, you get some more traffic, they do some more queries, get some more traffic, they do some more queries, and then at some point, your Postgres stops working. It slows down, it runs out of memory, all these kind of issues. So what are read replicas and how do they solve this? Instead, your clients do the write queries to your Postgres server, which is now called the primary because it does read and write traffic. And that primary, it will copy all the written data to the Postgres read replicas, which can be multiple servers, and those servers, they handle all the read queries. So this way, you split your queries across multiple servers, and you can sort of add servers when your load becomes too high for a single server to handle. And what is Citus? Why does it help with load balancing? Why does it not want load balancing? Well, that's because it's similar to read replicas, except that instead of only being able to load balance your read queries like you could with read replicas, you can now also load balance your write queries. All the servers in a Citus cluster, they can handle write queries, and the way that works is the tables, they're not actually there on all the nodes. All the data is not completely on all the nodes. Instead, it's what's called sharded. It's split across multiple nodes, and each node has like one node has user 1, 2, 3, and the other node has user 4, 5, 6. And if you send a query to the node where the data is not there, it will simply forward the query to the node where the data actually is. And that's done with these internal connections. So you can do reads and writes to all the nodes, and then the internal connections, they will sort of make sure that the data comes from the right place. And for this, you also need load balancing because you want to read and write to all the nodes. And one of the advantages of also being able to do writes is most of the time, most applications, they mostly care about reads. So it's like a large percentage of traffic is reads. But when you start doing like bulk imports, it's quite useful to be able to do those in parallel and scale that out and make it go a bit quicker instead of having to do that on one single node, because that might get exhausted if you do actually a lot of write traffic. So then the question is, how do you do this load balancing? Well, in general, there's two different approaches to load balancing. There's client-side load balancing, which means that the client that connects to the server, it knows about all the Postgres nodes. It connects to all of them, and it sends queries to a different one each time. That's pretty much how it works. And then there's server-side load balancing, in which the client doesn't actually know that there's multiple servers. Instead, the client connects to a single logical server, like a single IP, and that IP, it will behind the scenes, it will forward the request to different servers. So let's go a bit deeper into how client-side load balancing works. There's pretty much two different ways of implementing this. You have a hard-coded list of IPs or domains that you give to each client, and they choose one and send a query there. Or you have, in your DNS, you store multiple DNS records for a single domain. So when the client tries to get the IP for that domain, it gets a list of IPs back. And then it will choose one of them. And the way it can choose one of them is with like a smart client, which knows about this and chooses one, or with a round-robin resolver. Because normally when you request the IP for a domain, you ask the OS, like, hey, please connect me to this domain, and the OS will sort of handle it for you. And the problem is that sometimes, like, that part will need to know about, like, the choosing different ones. So you need what's called a round-robin resolver. It will iterate over all of them for new requests. So the downsides of this approach is that all the clients need to know about all the servers. You somehow need to get the data there. If you use the hard-coded list of IPs, you need to update all your applications when you add a new server or when you remove a server. So that's a bit of a hassle. So that's why the DNS approach works a bit better in that regard, because you can change the record on your DNS server, and if the clients work well, they will pick up the changes. Yeah, it doesn't happen always. It's very common that they cache this once. It's always DNS, yes. And another downside is that every client needs logic to be able to choose servers, which is also, it's extra logic on the client, so you need to install some stuff to make that work. And then the caching is like, if you add a server, even if to the DNS, if you don't refresh this list, it doesn't work. So 2 clients in the Postgres ecosystem, they support client-side load balancing. The Java client and the C# client, they support load balancing. And PG Bouncer, which is like a Postgres query proxy, it gets a query and it forwards it to Postgres. It has a support to forward it to different Postgres servers, but that only was added in March of this year. And libpq, which is pretty much the most used Postgres connection library. It's used under the hood in Python and Ruby and JavaScript and all kinds of other things, except for Java and C#, because they need their own thing. But that doesn't support client-side load balancing at the moment. I submitted a patch somewhat recently, and there's been some feedback on it, but overall it was good feedback, I think. So I hope that it gets into Postgres 16, but that's still like a year away from release, so it's not super helpful at this moment. And when you use the round-robin resolver, it means that you can do that even with libpq, because it will just resolve as long as the call to go from a domain name to an IP, it returns a different IP each time. That all works, but most operating systems, they don't do that anymore. They did in the past for some time, but the default resolvers, they will just pick the first one and return that to you. And so you always get the same on the same host, which is suboptimal, because then one host will always connect to one server, and that's not super nice. So then you would need to install a different resolver or configure your existing one to use this round-robin stuff. And that's possible, but we're sort of selling Azure and Postgres there. And what we've learned is that users, even technical users like yourself, they have a hard time setting stuff up. It's much nicer if they don't have to do anything. It's also a nicer experience, but even if it's not a super nice experience, people just don't read the docs, and it's fine. But then your load balancing doesn't work, because your resolver will just connect to the first one all the time. So what we kind of want is, we want a sort of a solution that works out of the box without people having to configure any OS stuff, and where we can handle sort of the hard parts. So that's where server-side load balancing comes in a bit. This is a different type of load balancing. So the client only connects to a single node, or a single IP or host name, and then it just works. That's the idea. And the way that's usually done is either with a proxy server, which is running some software to forward the query to different servers, or you can have software-defined networking load balancing, which is instead of having a dedicated server for this load balancing, you use the routers that are already in the network of the data center, and they will then yeah, route differently based on some heuristic. And the nice part of like this SDN type thing is that it doesn't need an extra server. It doesn't add some extra latency, because the proxy server adds some extra latency because you have an extra hop that you need to go to. So every query, it will go from here to here, and then it just takes a bit longer. And with this software-defined networking, you can just do what you normally did. That's kind of it. And the big advantage for us, at least, is that clients, they don't need any special configuration. You can just give people a host name and it works. At least that's what you would want. So there's two kind of ways of implementing this for Postgres. The server-side load balancing. One is you have a dedicated PG bouncer server. That's like the proxy server approach, where PG bouncer is running. Because it has the load balancing support, people can connect to it, and their queries will go to some other server. And the nice thing is that it understands the Postgres protocol, and you can even load balance based on transactions. So if they don't even one connection might go to different nodes, which can be helpful. But the problem is, again, it introduces some extra network latency. And even a bigger problem is that PG Bouncer is single-threaded. So you can imagine that if you have a problem that one Postgres server is unable to handle your load, then one core might have a problem handling all this traffic, even if it's just forwarding the queries. Because I mean that's fairly simple, but it still needs to handle all the TLS encryption on a single core. So it doesn't really scale. You start running into the problem that at some point PG Bouncer just becomes bottlenecked on one CPU core. One CPU core on your 32-core machine is maxed out, and still it doesn't go any faster. So this is not really a good solution. So the other approach is to use an off-the-shelf TCP load balancer. And TCP load balancers, they don't work at the Postgres protocol layer. They work at one layer lower. They send one TCP stream to one server and one TCP stream to another server. And the nice thing about this is that lots of people use them, so they have all kinds of nice and fancy features, like health checks. So if one of your read replicas is, I don't know, it crashed, the load balancer might detect that, and your queries just don't go there anymore. And because these are fairly common, there's also SDN load balancers for this, because the PG Bouncer, it's so specific to Postgres that there's no SDN support for that. But TCP load balancing, lots of people use it, so people made sure that the routers can handle that. So, well, this issue seems simple. Let's use an off-the-shelf TCP load balancer. Well, but yeah, sadly, it doesn't work like that. Because one very important assumption with TCP load balancing is all the TCP streams are independent. If you have a TCP stream that's dependent on another, and it might be sent to a different server that doesn't know anything about it. And sadly, that's exactly how cancellation requests in Postgres work. When you connect to Postgres, just your first connection to send some queries to Postgres, you connect to it with one TCP stream, which is black. And then Postgres, the first thing it does, it sends back, hey, thank you for connecting. If you send me a secret token 123, then I will cancel any query that's running on this connection. So you run delete from users. Oops, that's not what you wanted. You wanted to only delete like one specific test user, but you forgot the where clause. And you're like, oh no, this query is running way too long. Control C, so make it stop. And what your Postgres client then does is it opens a new TCP connection, that's shown in red, and it sends this cancellation token there. And Postgres is like, okay, I know this token. Let me cancel this query. It reports back on the other connection, like, well, we canceled it. You asked for to cancel this. It's canceled, no problem. And then you're happy, because you still have all your users. But the problem is, if you put a load balancer in between, it doesn't really work like that anymore. because, or not always at least. Because if you send like the delete from users, it will, and the connect and stuff, it will go to server A. And your cancellation token is a different TCP stream, so the load balancer might just decide to send it to some other server. And this server is like, I don't know about this token. That's probably a hacker. We can't trust this connection. I'll just close it. It's good. Let's ignore this. We don't do anything. So yeah, that doesn't work. So yeah, the core assumption of the TCP load balancer is broken by cancellation requests for Postgres, because the TCP streams are not independent. Same session, same TCP stream. New session, different TCP stream. But it's going wrong with cancellation requests because they depend on another TCP stream. And for the TCP load balancer to work, they shouldn't. But for cancellation requests to work, they should. So it's a bit of a problem there. So one workaround, like most of the time they will go to wrong server. So one workaround is just press Ctrl+C like a million times until it cancels the query. I mean, you'll probably do that anyway if you so it might be okay for you, but it's not optimal. So instead, you kind of want a solution to this problem, but at the moment, none really exist. So I came up with an idea on how to fix this, and I made some pull requests to have this, try to get this fixed. And the idea is to make Postgres servers know about each other. So instead of, like, if the query goes to server A and the cancellation goes to server B, instead of server B thinking, I don't know this is a hacker, instead it's like, I don't know this. It's probably meant for some other server. Let me just ask server A, send the cancellation there. Maybe they know what to cancel. And it sends it there, and the server A is like, I know it. I will cancel your query for you. So one Ctrl+C press, and it will work, which is super nice. But then, how do you actually? It's a nice idea, but how do you actually make that work? So one option is using Postgres extensions, because one of the nice things about Postgres is that you can create extensions. There's all kinds of hooks to hook into how Postgres works. It's what Citus uses for a lot of things, like to change how all the planner and stuff works. But sadly, there's no extension hooks for cancellation related code. There's no way to intercept what Postgres does when a cancellation comes in. So the only way to do that would be to fork Postgres, and we kind of don't want that. So one other way is to get hooks or like built-in functionality even into Postgres itself, but that takes a long time because Postgres releases, they happen once a year, and there's like a half a year feature freeze. So it usually takes like between half a year and a year and a half to get like something new into Postgres. And it also, even if you do that and you wait a long time, it still doesn't work for old Postgres versions. And our customers, they're sometimes using not the newest one. So yeah, it's for us, it doesn't really help that much. So, and another downside is we need to build this whole cancellation forwarding support into Postgres, which is, it's some work. You'd rather not do any work. So instead, another approach is we modify PG Bouncer. So PG Bouncer can run in front of any Postgres server version. As long as you get the newest PG Bouncer code, you can have some changes in there. And PG Bouncer, it's less impactful to upgrade. If you upgrade Postgres, you need to do stuff with data files, and you're down for a while. No one really likes that. It's not too hard, but it's still, upgrading your database is not a fun thing to do in general. So, and one advantage of PG Bouncer is it already has cancellation forwarding support, because think about it, it forwards queries, and it also needs to forward those cancellations that it gets. So there's already code to forward cancellations for forwarding to Postgres. The only change that really needs to be made is to forward it to a different Postgres, or to forward it to some PG Bouncer server. And I made a PR for this. I need to update it a bit, but it's working. So So how this then works is you run delete from users again. It goes through PG Bouncer on the server A, and that will forward it to Postgres on server A. And then the client will send a cancellation, and it will go to the PG Bouncer on server B. And that will think like, this is not for me, let me ask server A. It will forward it to PG Bouncer A, and that will forward it to Postgres, and you didn't lose your data. So, but then we get to the same problem. I mean, we discussed PG Bouncer already. It's single-threaded, so it's not very performant if you need high-throughput stuff. But the advantage is that here we're not having one PG Bouncer for all your nodes that you're connecting to. We have one PG Bouncer per node, so that already helps a lot. And the other, but even then, if you have a big enough nodes, you can still run into the problem where PG Bouncer becomes the bottleneck. Luckily, PG Bouncer also supports multi-process stuff, so you can run multiple PG Bouncer processes on the same port, which uses like a somewhat fancy feature that most people don't know about that it exists. Because usually when you run some software and you run it on a port and you run it again, like your operating system will say, no, I cannot do that, this port is in use. I'm fairly certain most of you have seen this error. But you can instruct the operating system not to complain about that. You can just run multiple things on the same port. The only thing is that then, the operating system will sort of randomly choose where your requests go. So for most things, that's not optimal. If you run two Postgres servers and they're completely independent, it's not nice if half of your data is in one and half of the data is in the other. So you need to be a bit careful. It's not something to turn on for everything, but for PG Bouncer, it makes a lot of sense. Because it's stateless, and as long as you forward to the same Postgres version of server in the end, it's all good. So you turn on the setting, Linux will pretty much be a second load balancer, in essence. It will load balance not across servers, but across PG Bouncer processes. And so we end up with a multi-layered load balancer, which looks a bit like this. You delete, it goes to Linux kernel, it goes to one PG Bouncer, and it goes to Postgres. You do cancel, it goes to another Postgres server, goes to PG Bouncer there. It's like, I don't know this. I'll go again to the Linux kernel on some other server, and it goes to the wrong PG Bouncer. And that PG Bouncer is like, I still don't know it. Let me forward it to a PG Bouncer on this node and see if they know it. And that PG Bouncer is like, yes, I know it. I will send it to Postgres. It's all good. And Postgres is like, canceled your query, no worries. Very easy. Just had to do like 20 hops to get there, but it's all good. So then there's one sort of final problem, which is, to which PG Bouncers should we forward it? Because now we're running 4, and if you have some more servers, with some more cores, you have some more and some more and some more. So, sending this cancellation to all of them, it's not very optimal. You have to open lots of connections, and it becomes a heavy thing to do. So the solution is quite simple. Inside the token that you get from inside the cancellation token, you encode like a tiny bit of like a node identifier, like a PG Bouncer identifier, and you let all the PG Bouncers know what the address is of each node ID, and they can forward it just to one, and it's all good. And that's the end, really. That works. now all the problems are solved.
That's worked. As easy as that. Awesome. Let me see if I see any questions. But we had a little incentive, right, for people that have questions.
If you have any good questions, you can get some socks, some free socks. If you dodge, that's a crazy good incentive. Anything free, it's what you want.
Yeah. Well, look, they're good. Should we,
Yeah,
can you display them?
Like I will.
Look at that.
Ta-da.
You will want those. So please toggle to the kleine zaal or shout out. It's fine. Like, we're not going to be difficult. I'm just going to repeat the question.
I have a question. So, if the Linux kernel is arbitrating and randomly distributing the connections to one of those PG Bouncer instances, how do you actually target the right instance, given the kernel is doing the distribution?
So yes. So the way that works is that when you use this reuse port thing, there's one important thing that you need to do. All the PG bouncers, they can listen on the same port, but they need to have a separate Unix socket that they also listen on. Because you also need to be able to I don't know, connect to it to do some operations sometimes. Just like you can connect to PG Bouncer on a separate database and do some PG Bouncer operations. So every one of them has a separate Unix socket. So on the ones on that machine, the way you specify the node ID host is you specify the Unix socket and then it works.
Perfect. Apparently it was a good question because he got socks, so that's good.
All right, yeah.
Jelte, can you repeat the question when you get it from
Sure,
the
yes.
Yeah, awesome.
Yeah, so if you can run multiple PC bouncers on one kind of virtual machine, can't you run them on different TCP ports and then create different kind of backend groups to the load balancer, the TCP load balancer, and that way you can basically just tell half of the request go to this backend group and half go to this backend group, and then you don't have to play around. You always know that how much traffic is going to go to which kind of PC bouncer.
Yes. Sorry, yes. So let's
you
repeat.
can summarize the question.
I will
it's
summarize the
fine.
question. Yes. So the question was, if you run all the PG bouncers on one machine on different ports, can you still do you still need some of this complexity? And I think you probably don't need like the SO reuse port sort of forwarding, but you will still need the other forwarding because if you have a load balancer in front, the cancellation might still end up at the wrong PG bouncer. So you won't need SO reuse port. You can run it on separate ports. But for us, it's also quite nice if customers can connect to PG bouncer directly. So we kind of want some static port for that.
If you have put load balancer,
You can do whatever, yes.
If you're using SO reuse port, what's the algorithm for who gets the message? The first available, round robin?
It's a bit of yes. So
Sorry.
yes.
Very annoying.
So the question was, if you use SO reuse port, what's the algorithm for choosing which process it goes to? It's a bit of everything, I think. There's not really clear documentation on how it exactly works, but it's a bit random. It's a bit like who responded quickly the last time. There's some. It's not really defined in the docs. I mean, it changes per Linux kernel version, basically. Read the source code if you want to know. That's the answer.
Fun, yeah.
Yes? Or yeah. You can go first. Yeah. Yes.
Sorry. So if you're actually going to change the structure of the cancellation tokens by adding this code for each node, doesn't it completely break backwards compatibility? Don't you have to reconfigure everything? Isn't that expensive?
So that's also a good question. So the question is, if you change the structure of the cancellation token by adding the node ID in it, do you need to change all the clients to know about that? And you would if you would actually change the structure visibly to the client. But the thing is, the cancellation tokens, they're like, I think 64-bit or 128-bit sort of random strings. Postgres uses like the first half for the PID and the second half for some random string for security. So you cannot cancel random backends that you don't know about. But PG Bouncer actually uses like the full 64 bits for random stuff. So instead, we now change, like we take, like, I don't know, like, I don't remember how many bits I chose, but like 12 or something. That seemed, I don't know, 16, I don't remember. Something that seemed like you're never going to have more than that amount of PG Bouncers. and you still have a lot of randomness left, more than Postgres usually has. So you can put it in, you can change it in a way that's backwards compatible for the client. That's the important part. Do you still have a question?
When you open a connection with Postgres on the load balancer, does it keep a track of the session from ID? Like when it opens, like let's say you fired like delete from user's query, so will it keep a track of the session on the load balancer itself, or?
Okay, so the question is, if you use the load balancer, does it keep track of the session somehow so that next queries go to the same Postgres server? So yes, because like one session, it's equivalent to one TCP stream. It's one TCP stream that's open. So like a TCP load balancer will make sure that all the data that's sent to over one TCP stream will go to the same node. Usually it's because it's the same port, the same source port and IP. It will sort of hash that and make sure it always goes to the same thing. But there's other ways of doing it.
If load balancer can keep a track of it, can we use that information to route or route the...
So the question is can we use that same information to route the cancellation queries? And the problem is that no, we cannot, because usually, I mean, if you set it up in a secure way, all these connections, they will use TLS, some encryption at least. So the load balancer cannot read the cancellation token. It doesn't know anything about it is working at a lower working at the TCP stream layer. So it doesn't know anything about these cancellation tokens. For the load balancer, it's like this cancellation token is just a new TCP stream. It can go wherever it wants to send it. It doesn't.
Also support using the same backend for the same source address. So if the source address is same, you can route the traffic to the same backend. So if your load balancer supports something like that, then it doesn't matter if it's encrypted.
So yeah, so what someone mentioned is if you only load balance by source IP, it will work because you usually will send cancellations from the same host. But then all the connections to Postgres will go to that same host. So if you want to load balance multiple connections from one host to different nodes, then that also, I mean, it's still not really what you want.
How many stocks are left?
I don't know.
Yeah, that pair, just that pair.
That pair.
So that's going to be the last question then.
Yeah, I'm just also asked by this QR, but probably we don't have time for this. Yeah, just a quick question. You talked about latency with server load balancing because we need to go through these nodes. And what do you think if we have high write queries? And what it would be better like to have client load balancer with maybe some cache, memory cache, with connection data to some node where it replicated, or to have this, how to say, server-side load balancer with additional latency.
So the question is, what do I think is better, server-side load balancing or client-side load balancing? Well, as most answers, it depends. It's
More about like how much latency is in between these clients.
if you use this SDN style server load balancing, you won't get that much latency extra because it uses the existing infrastructure and it doesn't have an extra hop. But I mean, it will usually cost some money because cloud providers, they want to make some money. Very strange. But yeah, it depends on your data, on how much control you have over your clients. Both have advantages, but it depends on your situation what's the best. And right now you cannot use client-side load balancing with libpq. So that's, I mean, if you use Python or Node.js or Ruby, there's only really server-side load balancing that you can do.